Hello, my dear students. The topic of discussion in this lecture are a few concepts regarding to convex sets. Those concepts are convex combination, convex hull, convex polyhedron, and simplex. On the last day, I was trying to give the geometrical essence of basic feasible solution. Towards the end of the last day's class, I was trying to find out the location of the basic feasible solution of this pair of linear inequalities. We have found the locations of the basic solution of this pair of inequalities are these possible locations A1, then A3, A5, A6 and A4. Then we filtered out the basic feasible solution of this pair of inequalities together with the non-negativity restrictions. We have found that the basic feasible solutions of this set are precisely the vertices, and corresponding to every vertex we will prove now mathematically that there is a basic feasible solution. So this correspondence of a basic feasible solution and the vertices of a linear inequality region will be proven in general in the n-dimensional Euclidean space. So for any given inequality region, linear inequality region, which will be presented by certain matrix form in this form ax less than equal to b together with x greater than equals to 0, or you take off the standard form ax equals to b together with x greater than equals to 0, will prove that the basic feasible solutions of this region, which is coming from a set of linear inequalities, are precisely the vertices of the geometric region in the n-dimensional Euclidean space corresponding to this set, corresponding to the set of points x is in Rn such that x equals to b, x greater than equals to 0. You find out the region, you figure out the region in that n-dimensional Euclidean space, and you will find that the vertices of the set are precisely the basic feasible solution. We are slowly going to prove this, and these basic feasible solutions are very important in solving linear programming problems, because we will also prove the fact, the fundamental theorem of linear programming problem, that if there exists a solution of a linear programming problem, then it must coincide with a basic feasible solution. So the solutions to find of a linear programming problem, it is just to find the basic feasible solutions or the vertices of the n-dimensional of the region in the n-dimensional Euclidean space given by this set of constraints. Fine. So to prove that, we need a few facts to learn, and those are these ideas that I will describe today in this lecture. Let's start our discussion with the idea of how can we characterize the vertices of a given inequality region in the two-dimensional space. In the two-dimensional space, let me suppose the variables are x1 and x2, and I have some inequalities. Let's suppose I have a matrix of order 2 by 2, capital A. It is a matrix of order 2 by 2, and x is having two components, x1 and x2. And let's suppose I am having this inequality, ax less than equal to b. Corresponding to this inequality, what is the region in this x1 x2 plane? We notice that as A is a matrix of 2 by 2, obviously we can just write it as, let's suppose A11, A12, A21, A22. You have two components in X, x1, x2, and also B has two components, let's suppose B1 and B2. Fine. And therefore this inequality here is component wise. That means this inequality is equivalent of A11, A11 x1 plus a12 x2 is less than equal to b1, a21 x1 plus a22 x2 less than equal to b2. Now corresponding to the first inequality, you have one half space of the line given by a11 x1 plus a12 x2 is equal to b1. So you identify the line a11 x1 plus a12 x2 is equal to b1, and one side of it, either this side or that side, will be your this inequality region. So one half space. Let's suppose this half space, this side is your inequality region corresponding to the first inequality. Similarly, corresponding to the second inequality, you will have another region. So let me suppose the another region is, let's suppose this much. This this side of the line a21 x1 plus a22 x2 is equal to b2. Fine. And therefore, what is the inequality? What is the region in the R2 space given by these two inequalities? It is nothing but the intersection of two half spaces. Fine. By half spaces we mean any of the side of the line. Fine. So here, so mathematically this less than equal to b1 gives us a half space. Fine. And in general, a half space in the n-dimensional Euclidean space is given by, in the n-dimensional Euclidean space, a half space is nothing but some expression like this: a11 x1 plus a12 x2 plus till a1 in xn. So it is some kind of expression like this: summation I is equal to 1 to n, then a1i xi is less than equal to some constant b1. This is a half space. One side of the plane given by this summation is equal to b1. Similarly, in R2, plane reduces to a line, and therefore any inequality region is just a half space. And therefore, if you have a pair of inequalities, therefore it will give us intersection of two half spaces. If you have m number of inequalities, then obviously you will have intersection of those m inequalities and intersection of the half spaces given by those inequalities. So ultimately it will give us the intersection of a finite number of half spaces is obviously either an empty set or it is a polygonal region, right? So geometrically, the feasible set of a linear programming problem, for a linear programming problem, as you know, the feasible set is given by, for a linear programming problem, it is a standing assumption in our lectures that we are referring the standard form of the linear programming problem. And the standard form of the linear programming problem that you all know by now is the following, that it is maximization of a linear function C transpose X subject to AX is equal to B together with X greater than equals to 0. This is the standard form, and you all know this X equals to B comes from certain inequalities where you are incorporating slack variable and surplus variables, and then you are getting this equality region. So this equality region, this feasible set that we call feasible set of the problem, set of all points x's such that x equals to b and x greater than equals to 0, this set is called as the feasible set or set of feasible points of the problem, this problem, linear programming problem, the standard form of the linear programming problem. And corresponding to this feasible set, we have the region in the n-dimensional Euclidean space, a polygonal region, right? And the vertices are precisely the kings, these kings of the polygonal region, right? And these vertices will show that for a given standard form of the linear programming problem, the vertices of the feasible region are nothing but the basic feasible solutions. Corresponding to a basic feasible solution, you will have a vertex. Corresponding to a vertex of the feasible region, you will have a basic feasible solution of this system of equalities x equals to b together with x greater than equals to 0. That is what we are going to prove. Now here, how do we mathematically present the vertices? So for a polygonal region, let's suppose I have a polygonal region like this. Let's suppose I am just considering a hypothetical polygonal region. Corresponding to this polygonal region, what are the vertices? Obviously, this is your polygonal region. All the points on the boundary as well as all these dotted points inside this polygon. And here you have the vertices are all these kinks, and these kinks are your vertices. Fine. And how do we mathematically present these kinks? You notice that these kinks or vertices are precisely those locations for which you cannot have a pair of points inside the set such that the line segment joining them is consisting that specific location. For instance, I am talking about, let's suppose, this point, and for this point you notice that you do not have any other pair of points for which the line segment joining them is consisting this point. For instance, I take a point over here, and for this cross point I have a pair of points. Precisely, you take this point and then consider the line segment joining them. The line segment is consisting this cross point. I take a point inside the region, then let me suppose I am taking a point over here, and I have a pair of points such that the line segment joining this pair of points is consisting this point. However, vertices are precise locations of the region such that you don't have any pair of points by which you will realize that the line segment joining that pair of points is consisting the location. Fine. And so this is your geometrical observation. How do we mathematically present it? So to present a vertex, obviously you need to express the line segment joining a pair of points. So let's suppose I have a pair of points x1, x2, and I wanted to find any point inside the mathematical expression or the algebraic expression of representing any point in between the line segment joining x1 and x2. Here is the point x1, here is the point x2. Say here x1, x2 both are points in, let's suppose, just in R2. And then let us try to figure out what is the algebraic expression of any point inside this x1, x2, inside this line segment. We notice that any point inside this line segment intersects the line segment into m is to n ratio, right? And therefore this point can be presented by, if I am denoting this point by x, then x can be presented as follows, that x is equal to m into x2 plus n into x1 divided by m plus n, or which can also be presented by m divided by m plus n. So it is just like if I am denoting lambda as my n divided by m plus n, so then you notice that it is lambda x1 plus m divided by m plus n will be 1 minus lambda into x2. Fine, where lambda is nothing but this positive fraction m divided by m plus n, and which lies in between 0 and 1. If lambda is equal to 0, then you are at the point x1. If lambda is equal to 1, then you are at the point x2, right? So this is how you can present any point inside a given line segment. Fine. So any line segment, if you can present by this expression lambda x1 plus 1 minus lambda x2, we can now mathematically define the notion of a vertex by if there does not exist a pair of points x1 distinct with x2 such that that location, let me suppose this location is V, such that V can be presented as lambda x1 plus 1 minus lambda x2, then we call V as a vertex, right? So this is a very simple way of representing a vertex. So let me slowly one after another, let me define a few concepts related to reaching at a vertex. Although this very simple definition will give you how to define a vertex, but in between I also wanted to explain several things regarding the inequality region or the constraint set of a standard linear programming problem. We note the following, that we have found that the feasible set of a standard linear programming problem is a polygonal region in R2 if x1 is having just two components or x is two dimensional. In that case, obviously it is a polygonal region, but if we have x3 variable, then this polygonal region will be a polyhedron region. Fine. And how do we define a polyhedron? Or specifically polytope, so some kind of definition, and for that we require a very specific notion called convex set. Why? You notice that the feasible region, the geometric region given by the constraint set x equals to b together with x greater than equal to 0 is having a very special thing, very special kind of observation, that you take a pair of points inside this polygonal region. Inside of this polygonal region, you take any pair of points and then you take the line segment, and you notice that the entire line segment is inside that polygonal region. Such a set is called a convex set. So let me define a convex set, and to define a convex set we require the notion of convex combination. This expression x equals to lambda x1 plus 1 minus lambda x2 is called convex combination of the pair of points x1 x2. This expression is also presented by lambda 1 x1 plus lambda 2 x2, where lambda 1 and lambda 2, both of them are greater than equals to 0, together with lambda 1 plus lambda 2 equal to 1. The same thing here, lambda is in between 0 and 1, by that obviously 1 minus lambda is also in between 0 and 1, so both of them are positive and their addition is equal to 1, right? Equivalent they are. This expression and this expression and this expression, they are the same identical expression. So and this expression is called as convex combination of the points x1 x2. If you have n number of points x1 x2 xn in the n dimensional Euclidean space, then the convex combination looks like the following. So I define the idea of convex combination very neatly, by which we will define the idea of convex set in the n-dimensional Euclidean space. For two-dimensional Euclidean space, the idea of convex set is very simple and clear to us, that you take a pair of points inside the set, and if you find that the line segment joining that pair of points is entirely lying inside of that set, and if this is happening for every pair of points inside the set, then we call the set a convex set. Fine. Geometrically everything is clear for R2 plane, but for Rn space we cannot geometrically observe it, and for that we require certain algebraic expression, and that algebraic expression is the following: the convex combination. Convex combination. By convex combination we mean the following, that let you have x1, x2, xp, p many points in the n-dimensional Euclidean space. Then the expression lambda 1 x1 plus lambda 2 x2 plus lambda p xp, where lambda p is greater than to 0, and addition of not just lambda p, it is every lambda I. Each of the lambda I is greater than equal to 0 for every I is equal to 1 to till p, and their addition lambda 1 lambda 2 lambda p, their addition is equal to 1. Then we call this expression lambda 1 x1 plus lambda 2 x2 plus likewise way up to lambda p xp, where these lambda i's restrictions are valid, non-negative, and addition up to 1. This expression is called as a convex combination of the points x1 x2 till xp. Fine. Now we define a convex set. A set is said to be convex a set let's suppose capital S, which is a subset of the n-dimensional Euclidean space, is called a convex set if for any pair of points x1 x2 in S, the line segment joining them, that is lambda x1 plus 1 minus lambda x2, is belonging to S for all lambda in between 0 and 1. Fine. So geometrically it says that a set S is convex if you take a pair of points. For instance, I just take a set of this type. Let's say this is my set, and here you notice that my set is set of all points on the boundary of this curve together with all these points inside. Fine. So here you notice that you take a pair of point, any pair of points, and then you consider the line segment joining them. You take a point even on the boundary, then you consider the line segment joining them. This entire line segment is lying inside the set S. So this set is a convex set. If I consider a set of this type, say set of all points on the boundary of this set and together with all the points inside this curve, then you notice that I have at least a pair of points, these 2 points, such that the line segment is not wholly inside the set, and therefore this set is not convex. So this is not a convex set, this is a convex set. So if I just take a triangular region, that is the boundary of this triangle as well as the inside of the triangle, it is a convex set. If I take a circular region, it is a convex set. Fine. Now I ask you a very special question, that is a singleton set convex? Is an empty set convex? Here you notice that a singleton set and empty set, they are indeed convex sets. This is due to the following. For empty set, you don't have anything to check here. You don't have any x1, x2, and therefore this statement is vacuously true. As in empty set there is no pair of points, there is nothing to validate, and therefore this statement is vacuously true. Therefore an empty set is always considered to be a convex set. Fine. And now try to talk about a singleton set. In a singleton set you just only have one point. So let me suppose this is my set, just one point. And then if you are considering a pair of points here, not necessarily this pair of points x1 x2 are to be distinct. So you just take x1 equal to the same point, this dot, x2 is also the same point, you take their convex combination, it is the same point. The line segment joining the same point is the very that point, right? And therefore a singleton set is also a convex set. Fine. And so let me just write it down here. The singleton set and an empty set are convex sets. Singleton set and empty sets are convex sets by definition. Fine. Now let me give you a few examples or a few results rather, on checking convex sets of a few special region in the R2 plane or even in the Rn space. So a few results. The first, you notice that a hyperplane, by hyperplane what do we mean? A plane in R3 space is given by this expression, that a1 x1 plus a2 x2 plus a3 x3 is equal to some constant c, real number c. This is a hyperplane. This is a plane in the R3 space. But if you have four variables, so you will have in the R4 space, in the four dimensional Euclidean space, a4 x4, and so all this expression a1 x1 till a4 x4 addition is equal to c. This is called as a hyperplane in the four dimensional Euclidean space, as if it is a stronger form of a plane. So that's why it is called as hyperplane. In the n-dimensional Euclidean space also, you will have then this expression is till a n x n is equal to c. This is a hyperplane. Fine. And this hyperplane is always a convex set. For instance, you just consider the two variable case, a line you have a1 x1 plus a2 x2 is equal to c, that is a line, and a line is a convex set because you take a point, you take a pair of points inside that line inside that line, and then you join the line segment joining those two pair of points, and that line segment is obviously inside that line, right? And therefore a line is always a convex set. A plane is also a convex set, and hyperplane is also a convex set. How do we prove it in general? So a hyperplane, which we denote by, let's suppose, S, set of all points in Rn such that you have some vector A transpose X is equal to C, where you have A is in the n-dimensional Euclidean space. The hyperplane S is a convex set. Sometimes it is also called a convex set in Rn, because this the geometric region here corresponding to the set capital S is a subset of the n-dimensional Euclidean space. Thus, it is also called a convex set in Rn. Fine. Here, let me just prove it. The proof is very simple. So here, let me just give a hint of it. You take a pair of points. Let's suppose I take x1, x2 in S, and once you take x1, x2 in S, so this will imply A transpose x1 is equal to C and A transpose x2 is equal to C. Here you notice that x1, x2 are not real numbers. they are vectors. X1 x2 in S you are taking, and S has points in Rn, therefore x1 x2 are vectors. A transpose x1 is therefore well defined. A transpose x2, because x2 is not a real number here, x2 is a vector, n dimensional vector. And once you have this, then you consider, so you have taken x1 x2 belonging to S, then what do you have to prove? You have to prove the following. Required to prove is that for any lambda in between 0 and 1, you should have that lambda x1 plus 1 minus lambda x2 is belonging to S. It has to happen for every lambda in between 0 and 1. Fine. So this is what you have to prove. Now to prove that this element is in set S, what do you have to prove? We have to prove that A transpose of this expression is equal to C. And you now compute A transpose of this expression, convex combination of x1 and x2. That is your lambda x1 plus 1 minus lambda x2. And if I just consider this, you will have lambda into A transpose x1 plus 1 minus lambda into A transpose x2, because lambda and 1 minus lambda are scalars, they are real numbers. So this is equal to now lambda times C, because A transpose x1 is C, plus 1 minus lambda times C, because A transpose x2 is equal to C, and therefore it is equals to C, and hence it proves that the set capital S is a convex set. Fine, very simple it is. And from here, similarly, you can prove the following, that half spaces, any half space or just a half space, and half space which is defined by capital H, defined by one side of a hyperplane, that is A transpose X less than equals to C, is convex. Prove it. Where A is a vector in the n-dimensional Euclidean space. Fine, and C is a scalar. C is a real number. And then next, the proof will be very similar here for the part 2, for this result 2. You just again take x1, x2 in S. So A transpose x1 is less than equal to C, and A transpose x2 is less than equal to C. And then you prove that A transpose of this expression is less than equal to C. Very simple it is. Because lambda and 1 minus lambda, those are non-negative quantities, so this inequality will be intact. And you just prove this on your way. Now I want to prove a very interesting fact, and which will be useful later on, that intersection of two convex sets, is it convex or not? It is indeed a convex set. Why? The reason is the following. Very simple it is to prove, although, but let me just sketch out. That let me consider two sets, S1 and S2 are convex. Fine. Once these are convex sets, what you will have is, now what do you have to prove? You have to prove the intersection is convex, S1 intersection S2. So to prove S1 intersection S2 is convex, we define the set, and you define S is equal to S1 intersection S2. Fine. Then you take a pair of points. Now you take x1, x2 is belonging to S. Suppose this. Then what we have to show? That convex combination of x1, x2 is belonging to S. So for any lambda, you have to show that lambda x1 plus 1 minus lambda x2 is belonging to S. That is what you have to prove. The proof is very simple, very trivial rather, because here you notice that S is S1 intersection S2, and therefore x1 x2 both of them are belonging to S1, and also x1 x2 are also belonging to S2. And once x1 x2 is belonging to S1, therefore this lambda x1 plus 1 minus lambda x2 is belonging to S1, separately also belonging to S2, and therefore this element is belonging to S1 intersection S2, and that's all done, right? But here is a point that you may have the fact that S1 intersection S2 is empty. So here, while assuming that x1 x2 are belonging to S, this might not be possible if S is an empty set. Fine. So here we discretize the proof into two parts. If S is empty, then trivially it is convex. Then it is evidently convex. If S is non-empty, then you suppose, starting with this, then suppose x1 x2 belonging to S, and then you prove that this lambda x1 plus 1 minus lambda x2 is belonging to capital S, and that is the proof of intersection of two convex sets is a convex set. Now I ask a question here: is union of two convex sets is a convex set? Is union of two convex sets a convex set? The answer is negative. That union of two convex sets may not be a convex set. For example, you take, very simply, you just take union of two circles. Let me consider very neatly, mathematically, let me present the sets. So let me take the union of this circle of unit radius centering at origin and unit circle centering at, let's suppose, 5 0. Fine. So these are two circles. Here is your 5 0 and here is your origin. Fine. And then these two sets are the following that you consider inside of these two region. So here is my S1, here is your S2. So consider, for example, consider S1 equals to this set of points in R2 such that x1 square plus x2 square is less than equal to 1, and capital S2 is set of points x1 x2 belonging to R2 such that x1 minus 5 square of it plus x2 square less than equal to 1. Fine. So these two sets you take, and their union, they are individually convex sets, but their union is not convex because you take a point in S1 and you take a point in S2, join the line segment, joining them, and there are many points which are not inside S1 union S2. Fine. And therefore the set S1 union S2 is not convex set, and therefore union of two convex sets may not be a convex set. However, intersection of two convex sets is always a convex set. Fine. Now once it is, then we have a very interesting fact that if you consider a set of inequalities, linear inequalities. So as a corollary now to the result that intersection of two convex sets is convex, then we can prove the following as a corollary, direct corollary, that the set this set of points, set of all points of this type x belonging to Rn, such that you have a finitely many inequalities, linear inequalities, that ax less than equals to b, that is the presentation of m many inequalities where A is a matrix of order m by n and B is a vector of m by 1 and x is also having n many components. So x is variable here. X is variable, but A and B, those are very fixed matrices, constant matrices. By constant matrices, I mean they are just matrices of real number as entries. Fine. So where A is a matrix of order m by n, B is the m vector, then this x less than equal to B is evidently intersection of the following, that intersection of all the m inequalities individually. So if I am writing AMN, this matrix has Aij as the ijth entry, then you notice that the first row of this ax less than equal to b is given by a11 x1 plus a12 x2 plus likewise till up to a1 n xn is less than equal to b1. Fine. If b has components bis, I is ranging from 1 to m, right? So the first component is b1, second component b2, and so on. Fine. So the first row of ax less than equal to b, this matrix inequality, will give us this expression a11 x1 plus a12 x2 plus till a1n xn less than equal to b1 as the first component. The second component will be a21, a22 till a2n, right? That will be the second row. And therefore, I just consider here the ith row of ax less than equal to b is just given by ai1 x1 plus ai2 x2 plus oa up to ain xn less than equal to bi. Fine. And here ax less than equal to b means the first inequality has to be satisfied by x and the second inequality of this x less than equal to b has to be satisfied by x and so on, right? So all the m inequalities are to be satisfied by x, then only you will say that x is inside of this set, right? And therefore it is intersection of I equal to 1 to m many inequalities are there, and for corresponding to every I, the set that I have written after the intersection, this is just a half space, and any half space is a convex set. So it is intersection of m many half spaces. So intersection of m many convex sets, and that will be convex again, because union of a pair of convex set is convex. And from the by just the similar logic here, just you take m many convex sets s1 intersection s2 intersection oa up to sm, then you can prove that intersection of m many convex sets is also convex. So intersection of finitely many convex sets is convex, and therefore this set, this is intersection of m convex sets, and those convex sets are just half spaces. Fine. And this is a convex set. So this is a convex set. The set, this is a convex set, right? So some linear inequality region. By linear inequality region, I mean where A is a matrix, B is also a vector, which also can be treated as a matrix m by 1. So this is called as linear inequality region, because each of the component of this inequality are given by linear functions on the left hand side. This expression, you notice, that is a linear function. Fine. And therefore it is called as, is x less than equal to b, is called a linear inequality, system of linear inequalities. Fine. So a system of linear inequalities is a convex set. We also have the another result. Let me name it as the fourth, right? And third, I now have fourth. Now you notice that the set, can you prove the following? The set, the feasible set of the standard linear programming problem, x is in Rn such that ax is equal to b and x is greater than equal to 0, is a convex set. This is very simple to prove. I am keeping you it as a home task. Very simple to prove. You take a pair of points x1, x2, and pair of points from this set. So ax1 plus ax1 equal to b and x1 is greater than equal to 0. Similarly, ax2 equal to b and x2 is greater than equal to 0. Then you prove that the convex combination lambda x1 plus 1 minus lambda x2 also satisfies both the restriction x equal to b and x greater than equal to 0, and that will prove that this set is a convex set. Very trivial experiment, very trivial calculation art, and you can all do this. Now let me take some more examples of convex sets in R2. Let me play with the convex combination of a few sets which are not very straightforward, and we have to apply a few inequalities, standard inequalities, so that you can then only check that, then only verify that the given sets are convex. For instance, I take the following example. Example 1, show that the set of points inside a circle, we know inside a circle all the points is convex, but can you prove it algebraically? Geometrically, it is very clear. So let's suppose I am taking x1 square plus x2 square is less than equals to, let's suppose, 16, is a convex set. Geometrically very clear to every one of us. Now can you prove this? How do we prove this? Algebraically, by that I mean you take a pair of points and then with the algebraic expression lambda x1 plus 1 minus lambda x2, you prove that that convex combination of x1 x2 is indeed inside of this set. How can you prove this? Well, so let me keep you this part also as a home task. You will play with this algebraic expression, convex combination. But let me neatly show the following, which is little bit difficult than example 1. So let me consider a parabolic region, so that the set of all points x1 x2 in R2 such that x2 square less than equals to x1. Fine. This is a convex set. Fine. How do we prove it? To show this, it is a convex set. We take a pair of points. So we now take a pair of points, like let's suppose y1, y2 and z1, z2, or p1, p2, q1, q2. So let you have p1, p2 belonging to this set. Let me denote this set by s. Belonging to s, and also the point q1 q2 is belonging to S. Fine. Then you have P2 square less than equal to P1, and also you have Q2 square less than equal to Q1, right? What do you have to prove? The convex combination of P1 P2 and Q1 Q2 is belonging to S. So now consider, uh, suppose, or we denote, let's suppose, by y1 y2 the convex combination of P1 P2. Lambda into P1 P2 plus 1 minus lambda into Q1 Q2 for some lambda in between 0 and 1. And notice that for lambda equal to 0, you have already assumed that for lambda equal to 0, you have y1, y2 is equal to q1, q2, and you have assumed that q1, q2 is in S. And therefore, in order to show that it is a convex set, we don't require to show that for lambda equal to 0 and lambda equal to 1, this expression is inside, this convex combination is inside the set capital S, because for lambda equal to 0 and lambda equal to 1, you have already assumed that those are points in capital S. So we don't have to prove for lambda equal to 0 and lambda equal to 1. And therefore, to prove that the set S is convex, it is sufficient to prove that this lambda P1 P2 plus 1 minus lambda Q1 Q2 is in S, capital S. And to prove that this is in capital S, what do we have to show? We have to show that y2 square is less than y1. That is what we need to prove. Let us now try to find what is y1 and what is y2. y1 is lambda p1 plus 1 minus lambda q1. y2 is lambda p2 plus 1 minus lambda q2, right? Now we take square of y2. Note that square of y2 square. We have to prove that y2 square is less than y1. What is y2 square? It is lambda p2 plus 1 minus lambda q2. q2 square. And let us play with this expression and let us check whether this is less than y1 or not. Fine. This expression is equal to lambda square p2 square plus 1 minus lambda square q2 square plus 2 lambda 1 minus lambda p2 q2. Fine. And then you notice the following. This is equal to lambda square p2 square plus 1 minus lambda q2 square plus we will write 2p2q2. This expression, you notice that by the arithmetic mean and geometric mean inequality, that am greater than equals to gm always, I apply this am, arithmetic mean and geometric mean inequality, for the elements p2 and q2. And then what will you have? You will have the following, that p2 square plus q2 square plus q2 square by 2 is greater than equals to under root of p2 square plus q2 square, right? And therefore that is under greater than modulus of p2 q2, and modulus of p2 q2 is always greater than or equal to p2 q2, right? So 2 into p2 q2 is always less than equals to p2 square plus q2 square. Fine. So 2 p2 q2 is less than equals to p2 square plus q2 square. And here this lambda into 1 minus lambda is positive. Therefore, this inequality will be still less than inequality region, less than inequality here. Fine. And once you have this is equals to, so as this p2 square plus q2 square by 2 is greater than equal to p2 q2, and you have lambda into 1 minus lambda greater than equal to 0, you have this inequality less than inequality is true. Now you notice that p2 square is less than p1 and lambda square is positive, so it is less than lambda square into p1 plus 1 minus lambda q2 square is less than q1 plus lambda into 1 minus lambda p2 square is less than p1 and q2 square is less than q1. And here all these lambda into 1 minus lambda, 1 minus lambda, lambda, all of these are your non-negative quantities, right? And therefore here you will have still less than inequality. And now let us just consider to simplify it. Now let us collect what is the coefficient of p1. Coefficient of p1 is lambda 1, lambda, and because lambda square plus lambda into minus lambda square, so it is lambda of lambda into p1. And for q1 you will have, just simplify it, you will get 1 minus lambda into q1. Fine. And that is what you wanted to prove, that this is equal to y1. Fine. And therefore y1 y2 is belonging to S, and hence by arbitrariness of the choice of lambda, and notice that we have chosen a particular lambda to find the expression of y1 y2, and this lambda was chosen arbitrarily inside 0 and 1. So for any lambda you choose in between 0 and 1, this y1 y2 accordingly you find, and you are observing that y2 square is less than y1, and therefore this convex combination lambda into p1 p2 plus 1 minus lambda into q1 q2 is inside the set capital S for any lambda in open 0 and 1, and that proves that the set S is convex. So therefore y1 y2 belonging to S, and hence by arbitrariness of the choice of lambda belonging to 0 and 1, the set S is convex. Fine. In a similar manner, you can prove that for the example 1, this set is a convex set. You just have to apply a similar inequality like an greater than equal to gn. Fine. Now next we will consider to discuss the concept of extreme point, convex hull, convex polyhedron, and simplex. Let me see how much time do I have. Oh, it is almost 1 hour. So let me now stop here. And on the next day, the topic of discussion are the topics those are left over today. Those topics are convex hull, convex polyhedron, simplex, and also we will define algebraically with some algebraic expression the vertices of polygonal region or vertices of a convex set. Fine. So with this I end up here. I stop here the lecture. I thank you all. Thank you all for all of your kind time to listen this lecture.